Something is happening on Venus right now that should not be possible. Not in the sense of violating physics, we do not think it is doing that. In the sense that every new measurement, every new mission, every new analysis of existing data keeps revealing things about Venus that do not fit what we thought we knew. Things that make planetary scientists stop and recheck their calculations because the results simply should not look like this. Let us start with what was just discovered, because there is a reason this documentary exists right now rather than 5 years ago. Something changed in our understanding of Venus very recently, and it is the kind of change that makes you look at that bright point of light in the evening sky differently. In 2023 and 2024, teams analysing archived radar data from the Magellan spacecraft, a probe that orbited Venus in the early 1990s, found something they were not looking for. They found that a volcanic feature on Venus had changed shape. Not the kind of change you can dismiss as measurement error. A vent feature near the massive volcanic structure Mart Mons had grown from a rough circular shape to a more oval shape, expanding by approximately 2.25 square kilometers between February and October of 1991. The volcanic conduit, the opening through which material can move, appeared to have changed dramatically over a period of 8 months. This was the first direct geological evidence of active volcanic activity on Venus in modern observational history. Not theoretical, not inferred from surface age statistics. Direct observational evidence that something changed. That Venus is geologically active right now. That the surface of Venus is not the static hellscape we had assumed it was. That something is moving underneath. And when you put this alongside everything else we know about Venus, everything that has been piling up for years, every anomaly, every unexpected measurement, a picture emerges that is genuinely unsettling. Because Venus should not be this strange. It is almost exactly Earth's size, almost exactly Earth's mass, 81% to be precise. It formed from the same primordial disk of material at roughly the same time, at not dramatically different distances from the Sun. By every expectation, Venus should be Earth's twin in the deeper physical sense, geologically similar, climatically somewhat similar, recognizably familiar. Instead, it is, in almost every measurable way, wrong. Not just different, specifically, systematically, deeply wrong, in ways that the more you examine them, the stranger they become. Tonight, we are going to go through the specific anomalies, the real measurements, the real data, the actual numbers, and follow them honestly to wherever they lead. Because the story of Venus is not just the story of a hellish planet. It is the story of a world that seems to be actively defying our understanding of how planets work. And some of what it is telling us is relevant not just to Venus, but to Earth and to every potentially habitable planet we are looking for elsewhere in the galaxy. If you are here because the night is long and you need something to settle into, stay. Venus is one of those subjects where the closer you look, the stranger it gets. And the strangeness is not on the surface, it goes all the way down. Let us start with the rotation, because this is one of the first things about Venus that tells you something is fundamentally unusual about this world. Every planet in the solar system rotates. The direction and speed of that rotation is determined primarily by the angular momentum that material had when it was swept together during planetary formation, by the spin imprinted on the forming planet by the chaotic collisions and accretion processes of the early solar system. In the absence of strong external forces, a planet should rotate in the same direction as it orbits the Sun, and it should rotate relatively quickly, because the conservation of angular momentum tends to spin up objects as they coalesce from larger, more spread out distributions of material. This is exactly what most planets do. Earth, Mars, Jupiter, Saturn, Neptune all rotate in the prograde direction, counterclockwise when viewed from above the Sun's north pole, and all rotate on timescales of hours to about a day. Even Uranus, which has a 98-degree axial tilt that effectively puts it on its side, still technically rotates in the prograde direction. Venus rotates retrograde, clockwise when viewed from above the North Pole, in the opposite direction from its orbit. The Sun rises in the west on Venus and sets in the east. This is not a minor peculiarity. It is a fundamental violation of what planetary formation models predict for a planet of Venus's size and position. Not only does Venus rotate in the wrong direction, it rotates extraordinarily slowly. One Venusian sidereal day is 243 Earth days. That is longer than Venus's year. A Venusian year is 225 Earth days. This is one of the most bizarre orbital facts in the solar system. Venus's day is longer than its year. It completes an orbit around the Sun before it completes a rotation on its own axis. And now the dimension that makes this even stranger. Venus rotates at almost exactly the right speed to keep the same face pointed toward Earth every time the two planets make their closest approach. The synodic period of Venus, the time between closest approaches to Earth, is 584 days. In that time, Venus makes almost exactly 2.5 rotations on its axis, which means that every time Earth and Venus are closest, Venus shows nearly the same face. Whether this is a gravitational resonance effect or a remarkable coincidence is actively debated. The origin of Venus's retrograde rotation is a major unsolved problem in planetary science. The most commonly invoked explanation is a giant impact. Early in solar system history, a large body colliding with Venus at the right angle and speed to reverse its rotation. This is the same class of explanation used for Earth's moon, a giant impact that both created the moon and set Earth's current rotation rate, and for Uranus's extreme tilt. Giant impacts were common in the early solar system and are a reasonable hypothesis for unusual rotational properties. But the giant impact hypothesis for Venus has problems. A giant impact large enough to reverse the rotation of a planet Earth's size would need to be an extraordinary collision, and the specific conditions required to produce exactly retrograde rotation at almost exactly the observed slow rate are very specific. Simulations struggle to reproduce the observed state. Every model requires fine-tuning that makes the outcome seem less like the result of a single collision and more like the result of multiple events or some other process. A more recent class of explanations involves atmospheric tidal torques. Venus's dense atmosphere, 92 times Earth's surface pressure, creates atmospheric tidal waves driven by solar heating. These atmospheric tides exert a torque on the solid planet. If the torque is in the right direction and the right magnitude, it could theoretically have slowed Venus's rotation and eventually reversed it. Models show this is physically possible in principle. Whether it actually happened and whether it can reproduce this specific observed rotation state is still debated. What makes the rotation problem particularly interesting is its connection to the mystery of Venus's changing day length, the measurement we mentioned at the start. If Venus's current rotation state is maintained partly by a dynamic balance between atmospheric tidal torques and solid body tidal interactions with the Sun, then that balance could shift as the atmosphere changes. Changes in atmospheric circulation, which we know happens on Venus with dramatic variability in the observed atmospheric dynamics, could produce measurable changes in the planet's rotation rate. This is the specific mechanism proposed to explain why Venus's day length appeared to shift by 6.5 minutes between the Magellan measurements in 1990 to 1992 and the Venus Express measurements in 2006 to 2008. The atmosphere changed, the torque balance shifted, and the rotation rate changed. Not dramatically in absolute terms, 6.5 minutes out of 243 days is about 0.002%, but measurably in a way that no model fully predicted. Let us now talk about the atmosphere, because the Venusian atmosphere is one of the most extraordinary environments in the solar system and contains several phenomena that are genuinely not understood. Venus's atmosphere is dense, extraordinarily dense. The surface pressure is 92 times Earth's, comparable to being about 900 meters underwater in Earth's oceans. It is composed of approximately 96.5% carbon dioxide and 3.5% nitrogen, with trace amounts of other gases. The surface temperature is approximately 465 degrees Celsius, not just hot, but stably, uniformly hot, maintaining this temperature on both the day and night sides of the planet, despite Venus's extremely slow rotation. This last point is remarkable. Earth has a day-night temperature difference of typically 10 to 20 degrees Celsius in many regions. Venus, despite having a 243-day night on one side, maintains temperatures on the night side within a few degrees of the day side. The atmosphere is such an effective heat reservoir and redistributor that the 243-day night on Venus barely registers in the temperature record. The sulfuric acid clouds that cover Venus completely at altitudes of 45 to 70 kilometers are what give Venus its characteristic brilliant appearance. They reflect approximately 70% of incoming sunlight, making Venus the brightest object in the sky after the Sun and Moon. These clouds are not thin wisps. They are thick, layered, continuous, completely obscuring the surface at all times in optical wavelengths. Every image you have seen of Venus's surface was taken by a radar system or a landed probe. You cannot see the surface of Venus with a regular camera from space. Within these cloud layers, the winds are extraordinary. While the surface is nearly calm, wind speeds of only a few kilometers per hour at the surface, largely because the dense atmosphere distributes momentum so effectively, at cloud altitude, the winds reach 360 kilometers per hour or more, flowing around the entire planet in about 4 Earth days. This atmospheric super-rotation, where the atmosphere moves dramatically faster than the planet rotates, is poorly understood. Models struggle to reproduce it. We do not have a complete physical explanation for why Venus's atmosphere races around the planet at a speed completely out of proportion to the planet's own rotation. Now let us talk about phosphine. Because this is one of the most controversial and fascinating chapters in recent planetary science, and it connects to the question of whether something genuinely unexpected, possibly even biological, might be happening in Venus's atmosphere. In September 2020, a team led by Jane Greaves at Cardiff University published a paper in Nature Astronomy announcing the detection of phosphine, pH3, a molecule of one phosphorus atom bonded to 3 hydrogen atoms, in the atmosphere of Venus. The detection was made using the James Clerk Maxwell telescope in Hawaii and confirmed with the ALMA telescope in Chile. The reported concentration was approximately 20 parts per billion, a small amount, but significantly more than any known abiotic chemistry on Venus should be able to produce. Phosphine is significant because it is extremely difficult to produce without either biological activity or very specific industrial chemistry. On Earth, phosphine in the atmosphere is produced almost exclusively by microorganisms, anaerobic bacteria that live in environments without oxygen. In the deep atmosphere of gas giants like Jupiter and Saturn, phosphine is produced by high-temperature, high-pressure chemistry in the deep interior and convected upward. But for a rocky planet like Venus, no known abiotic process can produce phosphine in detectable quantities in the atmosphere. The Greaves team was careful. They went through every known abiotic pathway for phosphine production on Venus: lightning, volcanic activity, photochemical reactions, delivery by meteorites, and none of them came close to producing the observed concentrations. The conclusion they offered, tentatively, was that either there is an unknown abiotic chemical pathway producing phosphine on Venus, or there is some biological source. The publication of this paper caused an immediate sensation. Headlines around the world announced the possible detection of life on Venus. Scientists immediately began scrutinizing the data. The scrutiny was intense. Several teams reanalyzed the raw spectroscopic data and found issues. The signal was initially reported at approximately 20 parts per billion, but on reanalysis, some groups found the signal was weaker, perhaps 1 part per billion, or potentially consistent with 0 within the error bars of the measurement. The specific spectral line being claimed as phosphine was adjacent to other molecular absorption features, making the separation difficult. The controversy has not been fully resolved. As of the latest analyses, most but not all researchers agree that the JCMT and ALMA data show some signal at the phosphine spectral line, but the magnitude is much more uncertain than the original paper suggested, and whether the signal is phosphine at all rather than sulfur dioxide at a different altitude remains contested. What this controversy revealed is something important about Venus. We do not understand its atmospheric chemistry well enough to confidently model what should and should not be present. The abiotic chemistry of Venus's atmosphere is poorly constrained. There are chemical reactions happening in those sulfuric acid clouds that we have not fully characterized. The phosphine controversy cannot be resolved without better data, specifically without direct sampling of the Venusian atmosphere at the relevant altitude. But the story does not end with phosphine. Because the phosphine controversy was part of a broader pattern of observations suggesting that Venus's cloud layers contain chemistry and possibly even structure that is not fully explained by our models. Let us talk about the unknown absorber, one of the oldest unsolved mysteries in the study of Venus. Venus's clouds, observed at ultraviolet wavelengths, show dark patches and streaks. These absorbing regions have been observed since the 1920s. They are among the oldest observations in the study of Venus. Something in the cloud layers absorbs ultraviolet light at specific wavelengths. This absorber accounts for approximately half of all the solar energy that Venus absorbs. It is not a minor feature. It is fundamental to the energy balance of the planet. The identity of this absorber has never been definitively established. Proposed candidates over the decades include sulfur allotropes, particularly S3 and S4, unusual short-chain sulfur molecules, ferric chloride, and various other chemical species. None of these explanations fully accounts for the observed absorption spectrum. The absorber has a specific spectral signature, specific spatial distribution, showing it concentrated in the upper clouds, specific temporal variability, showing it changes over days and weeks, and specific altitude dependence. In 2020, Sarah Seeger at MIT and her colleagues published a paper noting that the UV absorber's spectral signature is consistent with the absorption spectrum of microorganisms, specifically of dried bacterial spores. This is not evidence of life. Spectral similarity does not establish identity, but it adds to the peculiar picture of Venus's cloud layers, an unidentified absorber with properties that are consistent with biology, alongside the Phosphine controversy, alongside the decades of unexplained atmospheric chemistry. There is a more specific biological hypothesis for Venus that has received serious scientific attention. The idea that if life ever existed on Venus, it could potentially have survived in the cloud layers even after the surface became uninhabitable. The specific altitude range of approximately 48 to 60 kilometers in Venus's cloud layers has temperatures and pressures remarkably similar to Earth's lower atmosphere. Temperatures between 0 and 70 degrees Celsius, pressures between 0.4 and 1 atmosphere. These are conditions under which Earth life can survive. The hypothesis, first proposed seriously by Harold Moravitz and Carl Sagan in 1967, and recently revived by Seeger and others, is that microbial life could potentially survive in the cloud layers of Venus, protected from the lethal surface by the clouds themselves, metabolizing sulfur compounds, possibly accounting for the unknown UV absorber, possibly accounting for the phosphine signal. This is an extraordinary hypothesis. It requires that life originated on Venus when the planet was potentially habitable billions of years ago, that some organisms survived the transition to the current climate state by migrating to the cloud layers, and that they have persisted there for hundreds of millions or billions of years. Every one of these requirements is speculative. The hypothesis is not accepted mainstream science, but it is taken seriously enough by serious scientists to be part of the scientific motivation for multiple upcoming Venus missions. Let us now talk about what those missions are, because the scientific community has recognized that our current understanding of Venus is simply inadequate, and a wave of new missions is heading to the planet. NASA's Da Vinci mission, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is planned to send an atmospheric probe descending through Venus's atmosphere, sampling the chemistry at multiple altitudes for the first time since the Soviet Venera probes of the 1970s and 1980s. It will also image the highland regions of Venus from below the clouds, looking for evidence of ancient continental crust that might indicate Venus once had a more Earth-like geological history. NASA's Veritas mission, Venus Emissivity, Radioscience, INSAR, Topography and Spectroscopy, would map the Venusian surface at dramatically higher resolution than Magellan, looking for evidence of current volcanic activity, tectonic features, and surface mineralogy that might constrain the planet's geological history. It would determine whether Venus has active plate tectonics or something like it, whether there are currently active volcanic hotspots, and how young the surface actually is. The European Space Agency's Envision mission will study Venus across multiple wavelengths from orbit, looking at everything from subsurface structure to surface chemistry to atmospheric dynamics. It will have the capability to detect current volcanic activity through its radar and infrared instruments. These missions are motivated by a recognition that Venus is not a solved problem. It is one of the most mysterious objects in the solar system, our nearest planetary neighbour, almost our size, and yet exhibiting phenomena that no current model fully explains. Let us now talk about the geological mystery, about what the surface of Venus tells us and does not tell us about its history. The surface of Venus is young, dramatically young for a rocky planet. The density of impact craters on Venus's surface, when compared with the cratering rate from the early bombardment history, suggests that the entire surface was remade between approximately 300 million and 700 million years ago. Before that event, the surface record is essentially erased. Whatever Venus was like more than 700 million years ago we cannot read it from the current surface. This global resurfacing event is one of the most peculiar features of Venus. Earth continuously resurfaces itself through plate tectonics. Old seafloor is constantly being subducted and new seafloor created. So the average age of Earth's oceanic crust is only about 100 million years. But Earth's surface is not uniformly young. Continental crust can be billions of years old. Venus's surface appears to be uniformly young, the same age everywhere, as if the entire planet underwent a catastrophic resurfacing event simultaneously. The leading hypothesis is a kind of heat catastrophe. Venus lacks plate tectonics as Earth has it. The crust is not continuously cycling. Instead, the theory goes, Venus builds up heat internally until the lid of crust can no longer contain it, then undergoes a catastrophic overturn, massive flooding of the surface by volcanic magma, replacing the entire crust in a relatively short geological time, and then returns to a quiescent state as it cools again. Repeat this every few 100 million years. This model, called the catastrophic resurfacing model or the episodic tectonics model, makes specific predictions. It predicts that Venus is currently between catastrophic episodes, in a relatively quiescent state geologically. It predicts that the next catastrophic resurfacing event is at some unknown point in the future. And it predicts that below the current surface there might be remnants of older, pre-catastrophe material that could contain records of Venus's earlier history. But the 2023 discovery of apparent current volcanic activity, the changing vent shape in the Magellan data, complicates this picture. If Venus is currently geologically active, if volcanic activity is happening now rather than being confined to the catastrophic episodes, then the model of an episodically quiescent Venus is wrong. Venus might be more continuously active than we thought, with significant volcanism occurring during the so-called quiescent period. This matters for the question of Venus's current climate. Volcanic activity releases greenhouse gases, primarily carbon dioxide, water vapor, and sulfur dioxide. On Earth, volcanic CO2 is a major component of the carbon cycle, balanced by the carbonate-silicate weathering thermostat. On Venus, without liquid water and without the weathering cycle, volcanic CO2 would accumulate in the atmosphere without the natural sink that removes it on Earth. If Venus is currently volcanically active at a significant rate, it is continuously adding greenhouse gases to an atmosphere that cannot remove them. This means Venus's runaway greenhouse might not be a historical event that happened and then stopped. It might be an ongoing process, driven in part by continuing volcanism. Venus's climate might be actively getting worse right now, not just sitting in a stable, hellish equilibrium. Let us now talk about what Venus was, about the evidence suggesting that Venus had a radically different past, and about how and when the transition to the current state occurred. The hypothesis that Venus was once habitable, that it had liquid oceans, moderate temperatures, and potentially conditions compatible with life, is not fringe science. It is taken seriously by mainstream planetary scientists and is supported by several lines of evidence. The first line of evidence is isotopic. The ratio of deuterium to hydrogen, D/H ratio, in Venus's atmosphere is approximately 150 times higher than in Earth's oceans. This is highly significant. Deuterium is a heavier isotope of hydrogen. When water molecules evaporate from a planet's atmosphere and are dissociated by ultraviolet radiation, the lighter hydrogen atoms escape to space more easily than the heavier deuterium atoms. Over time, a planet that is losing its water will become enriched in deuterium relative to hydrogen. The extremely high D/H ratio in Venus's atmosphere is a chemical fingerprint of massive historical water loss. Venus had dramatically more water in the past and has been losing it for billions of years. The amount of water implied by the current D/H ratio, depending on the initial D/H ratio assumed, is consistent with Venus having had a global ocean, a genuine, substantial ocean of liquid water on its surface, for perhaps 2 to 3 billion years in its early history. The second line of evidence is climate modelling. Several teams, including a prominent 2016 study by Michael Way and Anthony Del Genio at NASA Goddard, ran general circulation models of an early Venus with a slower rotation, lower solar luminosity, and substantial water. The models found that under these conditions, Venus could have been climatically stable with liquid surface water for potentially 2 to 3 billion years. The same models suggest that as solar luminosity increased and Venus's rotation evolved, the climate became increasingly unstable, eventually crossing a threshold that triggered the runaway greenhouse effect. If these models are correct, and they are not universally accepted, they are one view among several competing models, then Venus was habitable for longer than multicellular life has existed on Earth. It is entirely possible that life arose on Venus in its habitable epoch, evolved for billions of years, and then faced the increasingly hostile conditions as the climate shifted. Whether any of that life survived the transition, whether microbial organisms could have adapted to the cloud environment as the surface became uninhabitable, is the central question behind the hypothesis of aerial biosphere on Venus. We genuinely do not know. But the question is physically grounded, scientifically motivated, and answerable in principle with the right measurements. Let us now talk about the specific evidence for current geological activity on Venus, about what the 2023 analysis revealed and why it was so significant. The key analysis was published by Robert Herrick and Scott Hensley in Science in March 2023. They compared radar images of Atla Regio, a volcanic highland region near the equator of Venus that includes Mart Mons, one of the planet's largest volcanoes, taken by the Magellan spacecraft in February 1991 and October to November 1991. The images were taken 8 months apart and at slightly different viewing geometries, which complicated the comparison. Despite the complication, Herrick and Hensley found a clear change. A volcanic vent on the northern slope of Sabas Mons, a smaller volcano near Mart Mons, had increased in area by approximately 2.25 square kilometers. Its shape had changed from roughly circular to an irregular oval with a floor that appeared to have subsided, suggesting that material had moved, either collapsed inward as an eruption drained the underlying magma chamber, or expanded outward as new material forced its way upward. The specific changes are consistent with a volcanic eruption or with the collapse of a vent following an eruption. They are not consistent with any other known geological process operating on these timescales. 8 months is an extraordinarily short time for significant geological change. On Earth, only active volcanic processes operate on this timescale. Critically, this discovery did not come from a new mission. It came from someone going back and looking at data collected 30 years ago with fresh eyes and better image processing tools. Magellan collected a tremendous amount of data during its 4 years of radar mapping between 1990 and 1994. Much of that data has been analysed, but the specific comparison that found the changing vent was not systematically done before. The image pairs were not well matched in viewing geometry, making comparison difficult, and the analysis required careful correction for those geometric differences. This raises the obvious question: What else is in the Magellan data that we have not found yet? If one systematic search of a subset of the data found one instance of apparent current volcanic activity, how many more might there be? How geologically active is Venus right now? The honest answer is that we do not know, and we need better data to find out. The Veritas mission, with its dramatically improved radar and the ability to take images of the same location multiple times, would be ideally suited to systematically search for current geological changes. The ESA Envision mission has similar capabilities. If either of these missions operates, we will have a much clearer picture of Venus's current geological activity within a decade. Let us now talk about something that has received very little attention outside the specialist community, but that dramatically changes the picture of what is happening on Venus: the discovery of unexplained chemical disequilibrium in Venus's atmosphere. Chemical equilibrium is the state where a chemical system has reached a balance, where the reactions producing each compound are balanced by the reactions consuming it. If you know the temperature, pressure, and composition of a gas mixture, you can calculate what the equilibrium chemical composition should be. Departures from equilibrium require an energy source continuously driving the chemistry away from equilibrium. On Earth, the most dramatic chemical disequilibrium is the presence of large amounts of oxygen in an atmosphere that also contains carbon, hydrogen, and reduced compounds. In chemical equilibrium, these would all react with oxygen. The atmosphere would trend toward carbon dioxide and water. The fact that Earth has abundant oxygen that is not reacting with everything is only possible because photosynthetic life is continuously producing oxygen faster than it is consumed. Venus's atmosphere is not as dramatically out of equilibrium as Earth's, but it has some puzzling disequilibria. The ratio of carbonyl sulfide, OCS, to other sulfur species in the lower atmosphere is higher than equilibrium models predict. The distribution of sulfur dioxide, SO2, with altitude shows anomalies inconsistent with simple photochemical models. The water vapor profile shows unexpected features. None of these disequilibria are definitive evidence of anything. They could represent unknown abiotic chemistry, reactions involving mineral surfaces, unexpected photochemical pathways, unidentified catalytic processes, but they are not explained by current models. Venus's atmospheric chemistry is richer and stranger than the models we use to understand it, and that richness, that unexplained complexity, is what makes the question of what is happening in those cloud layers genuinely open. Let us now talk about the Venera probes, about the extraordinary achievements of the Soviet space program in actually landing on Venus, and what those brief landings revealed. Between 1970 and 1985, the Soviet Union successfully landed 10 spacecraft on the surface of Venus as part of the Venera program. This is still the only time any spacecraft has successfully landed on and returned data from Venus's surface. The engineering achievement was extraordinary. Landing on a surface with 92 atmospheres of pressure and 465-degree temperatures requires extreme engineering, and most of the landers survived between 23 minutes and 2 hours before being destroyed. The landers took colour photographs, stunning images showing a rocky, flat landscape with angular rocks and reddish-orange illumination from the thick atmosphere filtering the sunlight. The light level was described as equivalent to a heavily overcast day on Earth, not completely dark, enough to see clearly. The rocks in the images appear relatively fresh and unweathered, an observation consistent with a geologically young surface. The landers also measured the surface chemistry. The rocks at the landing sites were basaltic, similar to the basalts that make up Earth's oceanic crust, produced by volcanic activity. This is consistent with a planet whose surface is dominated by volcanic processes. Perhaps most importantly, the landers detected the sound environment. Venera 13 and 14 carried microphones and recorded the ambient sound at the surface. The recordings show wind noise, relatively quiet given the dense atmosphere, and provide the only direct acoustic measurement ever made on another planet's surface until the Mars Perseverance rover deployed its microphone decades later. These brief, extraordinary windows onto Venus's surface are all we have for direct surface measurement. Everything else we know about Venus's surface comes from radar mapping from orbit, primarily from Magellan, and from models. The surface of Venus is poorly characterized compared to Mars, which has been visited by rovers for decades and comprehensively mapped in high resolution. This gap in knowledge is scientific embarrassment made physical. Venus is our nearest planetary neighbour. It is almost our size. It may have been habitable for billions of years. It is currently doing something geologically active, and we have not put a surface probe there since 1985. Let us now talk about what the recent analysis of Magellan data reveals about the broader question of tectonics on Venus, about whether Venus might have something like plate tectonics, operating at a different scale or in a different style from Earth's. The conventional wisdom has been that Venus lacks plate tectonics in the Earth sense. Earth's plate tectonics involves the creation of oceanic crust at mid-ocean ridges, the lateral movement of large plates, and the subduction of old oceanic crust at the edges of plates, creating the characteristic pattern of earthquakes, volcanic arcs, and mountain building at plate boundaries. This creates a global tectonic pattern that is recognizable from orbital data. Venus does not show this pattern. There are no clear mid-ocean ridge analogues, no clear subduction zones arranged in linear belts, no obvious global plate boundary system. The consensus was that Venus is a one-plate planet. Its outer layer is a single continuous shell rather than the fragmented system of plates that characterizes Earth. But recent analysis has complicated this picture. A 2023 paper by Paul Byrne and colleagues, analysing Magellan radar data, found evidence for what they describe as a patchwork of thin, mobile crustal blocks on Venus, regions of lowland plains that appear to have been jostling against each other, deforming at their margins in a pattern that superficially resembles a very early version of plate tectonics. The features look somewhat like what scientists believe Earth's tectonic system looked like in its earliest phases, a patchwork of thin, mobile blocks rather than the modern system of fewer, thicker plates. This finding, if it represents genuine tectonic mobility rather than some other geological process, would suggest that Venus might be in an earlier evolutionary stage of something like plate tectonics, rather than being fundamentally different in kind from Earth. It would connect Venus's geological history to Earth's in a way that the conventional one-plate model does not. It would also have implications for Venus's thermal evolution. Plate tectonics on Earth is one of the key processes through which the planet loses internal heat. Old oceanic crust carries heat to depth at subduction zones, eventually releasing it through volcanism, and the overall system provides an efficient cooling mechanism for the planet. If Venus has some form of crustal mobility that performs a partial version of this function, it changes our models of how Venus has been cooling over billions of years. Let us now talk about the question of Venus's interior. about what we can infer from indirect measurements and why understanding the deep interior is so important for understanding everything else. We have never sent a seismometer to Venus. We have very limited information about its interior structure. We know its overall mass and density from orbital mechanics. We have some gravity field mapping from Magellan that constrains internal mass distribution, and we have surface geology from radar mapping. That is essentially all. From these constraints, we can infer that Venus likely has a similar internal structure to Earth: a metallite core, a silicate mantle, a crust. The lack of a detectable magnetic field suggests that Venus's core is either not convecting in the way Earth's does, or is entirely solid, or has some other configuration that does not produce a self-sustaining magnetic dynamo. Earth's magnetic field is generated by convection of liquid iron in the outer core. Venus apparently lacks this. The absence of a magnetic field has profound implications. Earth's magnetic field creates the magnetosphere that deflects the solar wind, protecting the atmosphere from being stripped away by the continuous flow of charged particles from the Sun. This is exactly the mechanism that stripped Mars's atmosphere. Mars lost its magnetic field, lost its atmospheric protection, and lost most of its atmosphere to the solar wind. Venus, lacking a magnetic field, is exposed to the solar wind without this protection. Yet Venus has a thick atmosphere, 92 times Earth's surface pressure. How does Venus maintain such a massive atmosphere without the magnetic shield? The answer involves Venus's ionosphere, the electrically charged upper layer of the atmosphere. The ionosphere creates an induced magnetic field by deflecting the solar wind, not as effective as a true global magnetic field, but providing some protection. And Venus's atmosphere is dense enough that the solar wind stripping is happening, but has not yet depleted it significantly. But here is the disturbing implication. Venus is losing its atmosphere to the solar wind right now. Slowly, but measurably. The European Venus Express mission directly measured the rate of ion escape from Venus's upper atmosphere and found that Venus is losing a few hundred grams of atmosphere per second, roughly comparable to Mars's atmospheric loss rate. Over geological timescales, this loss rate matters. Venus's atmosphere may be slowly but continuously being eroded. If Venus was also losing water via this mechanism for billions of years, hydrogen and oxygen from water molecules being dissociated by UV radiation and the hydrogen escaping to space, this would be consistent with the historical water loss inferred from the D/H ratio. Venus once had more water. The water was lost. The D/H ratio records that loss. Let us now talk about something specific and underappreciated, about what the Venusian lightning question tells us about how poorly we understand the planet. Venus may or may not have lightning. This basic question has not been definitively answered. The case for Venusian lightning comes primarily from the Soviet Venera probes, which detected radio frequency emissions consistent with lightning discharges during their descents through the atmosphere. The case was strengthened by Venus Express, which detected a form of electromagnetic radiation called Whistler waves, a signature associated with lightning, in Venus's atmosphere. The case against, or at least for uncertainty, comes from the fact that Earth-based radio telescope searches for Venus lightning have not detected it, and from the theoretical difficulty of explaining where lightning would form in Venus's atmosphere. On Earth, lightning is produced in convective thunderstorms, where ice crystal and water droplet collisions separate electrical charge. Venus's cloud layers are sulfuric acid, not water. The charge separation mechanism might be different, or might not operate efficiently. Whether Venus has lightning matters because lightning is a significant driver of atmospheric chemistry on Earth. It converts nitrogen and oxygen into nitrogen oxides, produces ozone, and drives various reaction pathways. If Venus has lightning, it might be driving currently unmodelled chemistry in the cloud layers, potentially relevant to the unexplained chemical species detected there. The answer to whether Venus has lightning awaits direct measurement. No mission has carried the right combination of sensors at the right altitudes to definitively characterize Venus's lightning environment. This gap, this fundamental uncertainty about whether the planet has lightning, illustrates how incompletely characterized Venus is, despite being the nearest planet to us. Let us now talk about the broader significance of Venus's mysteries, about why understanding Venus matters beyond the intrinsic interest of the planet itself. Venus is the most Earth-like planet we know, in terms of size, mass, and initial conditions. If we cannot explain why Venus evolved so differently from Earth, why our twin became a hellish inferno rather than a second habitable world, we do not understand the factors that determine planetary habitability. And if we do not understand those factors, we cannot reliably evaluate the habitability of the thousands of exoplanets that are being discovered by missions like Kepler and TESS. The observable properties of exoplanets are limited. We can often measure their size, their mass, their orbital period, and in some cases, their atmospheric composition. We cannot directly observe their geological history, their tectonic regime, their internal heat budget, or most of the factors that determine long-term habitability. We rely on models, on theoretical frameworks that translate observable properties into inferences about habitability. Those models are calibrated on the planets we can study directly, primarily Earth, with important contributions from Mars and Venus. If our models of Venus are wrong, if there is something fundamental about how Venus became what it is that we have not understood, then those models are compromised. The errors in our Venus models propagate into our assessment of exoplanet habitability. Specifically, if Venus was habitable for 2 to 3 billion years and then underwent a runaway greenhouse triggered by the gradual brightening of the Sun, this is a data point about how common the runaway greenhouse transition is. It suggests that planets in the inner habitable zone can maintain habitability for long periods, but that there is a threshold, a brightening of the star threshold, beyond which the climate destabilizes. Knowing where that threshold is and what factors determine it is essential for identifying which exoplanets are currently habitable and which might have been habitable in the past. Venus tells us that habitable worlds can become uninhabitable, that the transition is real, that it has happened at least once in our solar system, and that understanding it requires understanding Venus. Let us now talk about what the sulfuric acid clouds of Venus actually are, about the specific chemistry of the cloud layers and why they are so scientifically interesting beyond their dramatic visual appearance. Venus's cloud layers extend from approximately 45 to 70 kilometers altitude, with distinct lower, middle, and upper cloud layers having different particle sizes and compositions. The dominant cloud particle is sulfuric acid, H2SO4, in concentrations of 75 to 96% mixed with water. These particles range from sub-micron in the upper haze to about 7 microns in the lower clouds. The sulfuric acid is produced by photochemical reactions in the upper atmosphere involving sulfur dioxide, SO2, and water vapor in the presence of ultraviolet radiation from the Sun. Sulfur dioxide rises from the surface through volcanic activity, reacts with water and UV light, and forms sulfuric acid droplets that condense into the cloud layers. This is a continuous chemical cycle driven by volcanism below and photochemistry above. But the cloud layers are not compositionally uniform. Below the main cloud deck, there is a lower haze layer where the chemistry is less well characterized. The particle sizes in this layer are larger than in the main cloud deck, and their composition is less certain. Some analyses have suggested that particles in the lower cloud and haze layer have properties inconsistent with pure sulfuric acid. They may contain other materials mixed in. It is in this lower haze and lower cloud region, approximately 48 to 60 kilometers altitude, where the temperature and pressure conditions are most Earth-like. And it is in this region where the unexplained UV absorber is concentrated, where the phosphine was reportedly detected, and where any hypothetical cloud-dwelling organisms would most plausibly exist. The chemistry of this altitude range is driven not just by photochemistry. At these altitudes, UV penetration is limited by the cloud layers above, but by thermochemistry, and possibly by heterogeneous chemistry on particle surfaces. The sulfuric acid droplets provide reaction surfaces. The temperatures are moderate enough for liquid phase chemistry. The available chemical species, hydrogen sulfide, carbonyl sulfide, sulfur dioxide, water, provide potential energy sources for chemosynthetic metabolism. This is not a claim that life exists at these altitudes. It is a characterization of why the altitude range is chemically interesting, and why the measurements of unusual chemistry there are scientifically significant, even without invoking biology. Let us now talk about something that the general public rarely hears about, but that is one of the most scientifically significant aspects of Venus: the question of whether Venus might have subsurface oceans or other liquid environments. On Earth, life is found anywhere there is liquid water, including in extreme environments kilometers underground, in frozen ice, in highly acidic conditions, in highly alkaline conditions, at temperatures above boiling and below freezing, under pressure. The discovery that life is so adaptable has expanded our sense of where life might be found in the solar system. Venus's surface is far too hot and under far too much pressure for any known form of life. But what about the subsurface? Could there be environments in Venus's crust or upper mantle where conditions are less extreme? Theoretically, at sufficient depths in Venus's crust, temperatures might be moderate enough for liquid water to exist, if there is any water left in the crust. The surface temperature is 465 degrees, but temperature decreases with altitude above the surface. This is why the cloud layers at 48 to 60 kilometers are relatively cool. Similarly, below the surface, temperature increases with depth as you approach the hot interior, but at some shallow depths, the temperature might be in a range where liquid water could exist under high pressure. The problem is that Venus is extremely dry. The D/H ratio, while indicating historical water loss, shows that Venus today has very little water. Without water, the possibility of liquid water environments in the subsurface is minimal. But there is another possibility. Sulfuric acid is not only the composition of Venus's clouds, it may be present as a liquid in some surface and shallow subsurface environments. Sulfuric acid remains liquid over a wide temperature range. Certain microorganisms on Earth survive in concentrated sulfuric acid. If Venus has sulfuric acid environments, which it almost certainly does given the cloud chemistry, these might in principle harbour life, though no known Earth life could survive the specific combination of high temperature, high pressure and concentrated acid that characterizes the Venusian surface. Let us now talk about what all of these mysteries, the changing rotation, the unknown UV absorber, the phosphine controversy, the apparent current volcanism, the potential ancient habitability, the unexplained atmospheric chemistry, what they collectively suggest about Venus. They suggest that Venus is one of the most incompletely understood bodies in the solar system. Not because it is far away or hard to observe, it is our nearest neighbour, the brightest object in the sky after the Sun and Moon, the target of dozens of missions going back to the 1960s, but because the questions it poses are genuinely hard, and the data needed to answer them has not yet been collected. Every question about Venus connects to every other question. The rotation is connected to the atmospheric dynamics, which is connected to the unknown UV absorber, which might be connected to the atmospheric chemistry, which is connected to the question of biological or abiological processes, which is connected to the history of habitability, which is connected to the volcanic activity, which is connected to the interior dynamics, which is connected to the absence of a magnetic field, which is connected to the historical water loss, which is measured by the D/H ratio. Venus is a system, and we are trying to understand the system with incomplete measurements of individual components. Every new measurement changes the picture. Every new analysis of existing data, like the Herrick and Hensley volcanic activity discovery from archived Magellan data, reveals that the picture is more complex than we thought. This is what makes Venus genuinely exciting as a scientific target right now. Not because we have found life, not because we have solved the rotation mystery, but because the combination of new analytical techniques applied to existing data, combined with the imminent arrival of new missions designed specifically to address Venus's outstanding questions, means that the next decade is likely to be the most scientifically productive era in the history of Venus exploration. We are going back to Venus, and when we arrive with modern instruments, with the seismometer that has never been deployed there, with the atmospheric probe that will sample the chemistry directly, with the radar mapper that will detect current geological changes, we will almost certainly find things that surprise us. Because Venus has a history of surprising us. Everything we know about it is strange. Let us talk about something specific that happened in 2021 that reshaped the scientific conversation about Venus, and that had nothing to do with any new mission or new observation. It had to do with looking more carefully at data we already had. The Magellan spacecraft carried a radio science experiment that measured the gravity field of Venus by tracking tiny changes in the spacecraft's velocity as it orbited. Regions of higher density beneath the surface pull on the spacecraft slightly more, causing detectable changes in its orbital speed. Over 4 years of orbital mapping, Magellan built up a gravity field model for Venus covering most of the planet. This gravity data sat in archives, analysed at the time, and then largely set aside as the scientific community moved on. In 2021, a team led by Suzanne Smrekar at JPL went back to it with a specific question. Could the gravity data be used to identify regions of the crust that were thermally elevated, hotter than the surrounding crust, in a way consistent with current volcanic activity? The physics is this: hot rock expands slightly. A region of crust that is being heated from below by a magma plume will be slightly less dense than surrounding cooler crust. This density difference should be detectable in the gravity field. Less dense crust produces slightly less gravitational pull. By combining the gravity field data with the topographic data from Magellan's radar, the team could calculate what the expected gravity signal from topography alone should be, and then look at the residual, the gravity signal that cannot be explained by topography alone and must reflect internal density variations. They found anomalies. Specifically, they found 37 volcanic features on Venus that showed gravity residuals consistent with thermal uplift, with hot, buoyant material beneath the surface. These features are interpreted as active hotspots, places where volcanic plumes from the interior are currently impinging on the base of the crust, heating it from below and potentially driving current volcanic activity at or near the surface. 37. Not one or two, 37 locations on Venus where the combined gravity and topography data suggests active volcanic plumes beneath the surface. This does not prove current eruptions at all 37 sites. The gravity data is averaged over the entire Magellan mission and cannot detect changes over time. What it shows is that these regions have the thermal structure characteristic of active volcanic systems, the same kind of structure we would expect to see at Hawaii or Iceland on Earth, where mantle plumes are actively feeding surface volcanism. Combined with the Herrick and Hensley finding of an apparently changed volcanic vent, a specific, localized observation of a changed surface feature, the Smrekar team's finding paints a picture of Venus as a planet with widespread, ongoing volcanic activity. Not the dormant, episodically catastrophic world of the conventional model, but a continuously active world that is constantly being shaped by volcanic processes. This changes everything about how we think about Venus's atmospheric chemistry. If there are 37 or more active volcanic hotspots on Venus, they are continuously outgassing, adding sulfur dioxide, water vapor, carbon dioxide, and other volcanic gases to an atmosphere that is already in a peculiar chemical state. The unexplained features of Venus's atmospheric chemistry, the SO2 distribution anomalies, the carbonyl sulfide levels, the unknown UV absorber, might all be connected to this ongoing volcanic activity in ways that our models, built with the assumption of limited current volcanism, have not captured. Let us now talk about the specific question of what Venus's interior looks like, and why the absence of a seismometer on Venus for all these decades is one of the most significant gaps in solar system science. We have seismometers on the Moon. The Apollo missions deployed them, and they operated until 1977. We have had a seismometer on Mars since 2018, when InSight landed. The InSight seismometer fundamentally changed our understanding of Martian interior structure, revealing a crust that was thicker and more heterogeneous than models predicted, a mantle that was different in composition from expectations, and a core that was surprisingly large and liquid. Venus has never had a seismometer, not one. Despite being our nearest planetary neighbour and our closest geological analogue, despite being the target of dozens of missions going back to the 1960s, despite being geologically active, as we now believe, and therefore producing seismic events that would be measurable. The reason is engineering. Deploying a seismometer on Venus's surface and operating it for any useful length of time requires surviving 465 degrees and 92 atmospheres of pressure, conditions that destroy conventional electronics in hours. The longest-lived Venera surface mission survived 2 hours and 7 minutes. A seismometer needs to operate for months to build up a statistically meaningful catalogue of seismic events. This engineering challenge is not insurmountable, but it is genuinely hard. 2 approaches are under development. The first is high-temperature electronics. Electronic components made from silicon carbide rather than silicon, which can operate at temperatures above 500 degrees Celsius. NASA Glenn Research Center has been developing these components for years, and laboratory testing has demonstrated operation at Venus surface temperatures for extended periods. The second approach is insulation, building a thermal capsule that keeps the seismometer cool enough to operate using conventional electronics, managing the heat leak over the operational lifetime. Both approaches face the pressure challenge as well. 92 atmospheres requires extremely robust pressure vessels. But the pressure engineering is arguably more tractable than the thermal engineering. Submarines operate at comparable pressures on Earth, though for very different reasons. A seismometer on Venus would tell us the thickness and structure of the Venusian crust, the composition and layering of the mantle, the size and state of the core, whether it is solid or liquid, whether it has an inner and outer core analogous to Earth. These measurements would fundamentally constrain our models of how Venus formed and how it has evolved. More specifically, they would tell us whether Venus's core is convecting, and therefore whether it should be generating a magnetic field. If seismic data shows that Venus's core is liquid and capable of convecting, but there is no magnetic field, that tells us something fundamental about what is different about the dynamics of Venus's interior compared to Earth's. If the seismic data shows a largely solid core, that would explain the absence of the field through a different mechanism. The absence of seismic data from Venus is a scientific blind spot, so significant that every model of Venus's interior is essentially unconstrained by direct measurement. We are extrapolating from Earth's interior structure to Venus's based on the similarity of their sizes and masses. But the very evidence before us demonstrates that Venus and Earth are not simply similar. They diverged dramatically. Understanding why requires knowing what happened inside. Let us now talk about the radar mapping mystery, about specific features on Venus's surface that have resisted all attempts at explanation. The most puzzling class of Venusian surface features are called tesserae. These are elevated ancient terrains characterized by highly deformed intersecting ridges and grooves, a chaotic cross-hatched pattern that makes them look fundamentally different from the volcanic plains that cover most of Venus's surface. The name comes from the Greek word for tiles, because the intersecting linear features create a tile-like pattern visible in radar images. Tesserae are old. Their high crater density, relative to the surrounding volcanic plains, indicates that they predate the global volcanic resurfacing event, making them the oldest exposed terrain on Venus. They are the fragments of whatever Venus's surface looked like before the catastrophic overturn that remade the planet hundreds of millions of years ago. What are they made of? This is where it gets interesting. On Earth, the closest analogue to tessera terrain in terms of geological age and deformation style might be ancient continental crust, the kind of heavily deformed metamorphic terrain that makes up the cores of ancient cratons. On Earth, ancient continental crust is made primarily of granitic rocks, which require liquid water and specific pressure-temperature conditions to form. If Venus's tesserae are compositionally similar to Earth's ancient continental crust, if they contain granitic or at least intermediate composition rocks rather than the basaltic rocks that dominate Venus's volcanic plains, this would be extraordinary evidence that Venus once had liquid water, plate tectonics, and geological processes similar to Earth's early history. Magellan's radar cannot determine the composition of the tesserae directly. Radar measures surface roughness and reflectivity, not mineralogy. The compositional question requires either direct sampling of tessera rocks, which requires landing in a tessera region, which no mission has done, or high-resolution infrared spectroscopy from orbit, which can potentially distinguish different rock types through their thermal emission spectra. The Da Vinci mission includes an imaging component specifically designed to look down at the Tessera terrain at Alpha Regio during the probe's descent through the atmosphere. While the probe's primary mission is atmospheric chemistry, its camera system will be able to take the first high-resolution images of Tessera terrain from below the clouds. Not quite surface-level imaging, but much better than the radar maps available from orbit. The Veritas mission would include an infrared mapping capability that could potentially constrain the composition of the tesserae. If Veritas data shows that tesserae have compositional properties consistent with granitic or intermediate rocks rather than basalt, this would be the first remote sensing evidence that Venus once had continents. Once had the kind of geological diversity that on Earth is associated with active plate tectonics and the presence of liquid water. This single measurement, the composition of the tesserae, could potentially transform our understanding of Venus's history from a planet that was always somewhat Earth-like at the surface but always too hot, to a planet that had continents, had oceans, had plate tectonics, and lost all of it through the runaway greenhouse transition. Or it could confirm that the tesserae are just ancient basalt, very old volcanic rock, not continental crust. In which case, the Venus habitability story would need a different telling. Let us now talk about the specific question of cloud-level habitability in more technical detail, about what the constraints actually are, and whether the chemistry and physics of Venus's cloud layers are compatible with life. The habitability case for Venus's cloud layers rests on several specific observations. Temperature and pressure at 48 to 60 kilometers altitude are compatible with Earth life. This is correct and well established. The temperature range covers 0 to about 70 degrees Celsius, and the pressure range of 0.4 to 1 atmosphere is similar to Earth's surface. This is the strongest part of the case. The challenges begin with the chemistry. Venus's cloud layers are largely composed of concentrated sulfuric acid, 75 to 96% H2SO4. This is far more acidic than any environment on Earth where life flourishes. The pH equivalent of 96% sulfuric acid is extremely negative, around -12, compared to the most acidic environments where Earth life survives, which are around pH 0 to -1. The specific biochemical problem is that sulfuric acid destroys most biological molecules. It catalyzes hydrolysis of proteins and nucleic acids, and it reacts destructively with lipids that form cell membranes. However, some researchers, including Dirk Schulze-Makuch and Louis Irwin in their book Examining the Limits of Life, have proposed that life in Venus's clouds would need to use completely different biochemistry from Earth life. Rather than water as a solvent, such life would need to use sulfuric acid as a solvent, a concept called non-aqueous biochemistry. In principle, biochemistry in concentrated sulfuric acid is not thermodynamically impossible, but no example of such biochemistry has ever been identified, even in laboratories searching for extremophile organisms. The energy question is also challenging. Earth life uses various energy sources: sunlight, chemical redox reactions, organic compounds. In Venus's clouds, sunlight is available, but it is absorbed primarily by the sulfuric acid haze particles, making photosynthesis difficult. Chemical redox reactions using the available sulfur compounds are theoretically possible. Sulfur dioxide and hydrogen sulfide are both present, and their reaction produces elemental sulfur and water, releasing energy. Certain terrestrial microorganisms use sulfur chemistry for energy. Whether this chemistry is accessible in concentrated sulfuric acid at Venus cloud conditions is unknown. Water availability is the third challenge. Life as we know it requires liquid water. In Venus's cloud layers, water is present but at very low concentration. The clouds are sulfuric acid, not dilute acid. Water activity, the availability of water for biochemical reactions, is extremely low. Some extremophile organisms on Earth can survive at very low water activities, but none approach the conditions in concentrated sulfuric acid. So the honest assessment is Venus's cloud layers are not hospitable to Earth life. The temperature and pressure are fine. The chemistry is severely hostile. Whether life using fundamentally different biochemistry could exist there is a genuinely open question, but answering it requires either finding such life or establishing that the physical and chemical constraints make it impossible. We cannot rule out non-aqueous biochemistry because we do not have a theory of life general enough to prove that water is strictly necessary, but we also have no evidence for it. The phosphine question, if the phosphine is real and cannot be explained abiotically, would be the first piece of evidence that something interesting is happening at these altitudes. The UV absorber, if it cannot be explained by known chemistry, adds to that. But neither of these is definitive evidence. Both could have abiological explanations not yet identified. Let us now talk about something that connects Venus to the broader question of where we are looking for life in the universe, about how Venus changes the calculation for habitability around other stars. The traditional picture of planetary habitability focuses primarily on liquid water, on whether a planet orbits in the zone where its surface temperature allows liquid water. This zone, called the habitable zone or Goldilocks zone, is bounded on the inner edge by the runaway greenhouse, the point at which the planet gets too hot and water is lost, and on the outer edge by freezing conditions. The inner edge of the habitable zone is where Venus lives. Venus is just slightly inside what we would traditionally calculate as the habitable zone for the Sun. The question of exactly where the inner edge is, how close to a star a planet can be and still retain liquid surface water, is one of the most important questions in astrobiology. And Venus is the single most relevant test case for that question. Before we understood that Venus might have been habitable for 2 to 3 billion years, the conventional assumption was that Venus was always too close to the Sun for habitability, that the inner edge of the habitable zone lies somewhere between Venus's orbit and Earth's. If Venus was habitable for billions of years, the inner edge of the habitable zone is significantly closer to the Sun than previously thought. This dramatically increases the number of potentially habitable planets around other stars, planets that we might have previously dismissed as too hot might actually be within the habitable zone. Conversely, if we can understand the specific mechanism that ended Venus's habitability, the specific threshold at which the runaway greenhouse kicked in, we can use that to better constrain where the inner edge of the habitable zone actually is. This would allow us to more accurately assess which exoplanets in the inner regions of their stars' habitable zones are likely still habitable and which might have already crossed the runaway threshold. The James Webb Space Telescope is already beginning to characterize the atmospheres of exoplanets in or near the habitable zones of their stars. The TRAPPIST-1 system, 7 rocky planets around an ultra-cool red dwarf about 40 light-years away, includes 3 planets in the habitable zone and is a primary target for atmospheric characterization. Understanding what a runaway greenhouse looks like from the spectroscopic signatures Webb can detect, using Venus as a template, directly improves our ability to interpret what Webb tells us about the TRAPPIST-1 planets and others like them. Every improvement in our understanding of Venus is an improvement in our ability to assess habitability elsewhere. Venus is not just a cautionary tale, it is a calibration point. The one rocky planet we know definitely underwent a runaway greenhouse transition at a specific distance from a specific star at a specific epoch in solar system history. Understanding the details of that transition tells us where the boundary is between habitable and uninhabitable, and that boundary is what we need to know when we look at the growing catalogue of exoplanets and try to decide which ones to study more carefully. Let us now talk about the peculiar question of Venus's lack of a moon, about what the absence of a large satellite might mean for the planet's history and habitability. Earth has the Moon, a large satellite that, as we have discussed in the context of lunar history, stabilizes Earth's axial tilt and has contributed to Earth's habitability in various ways. Mars has two tiny moons, Phobos and Deimos, which are probably captured asteroids too small to have any significant gravitational effect on Mars's rotation or axial tilt. Mercury has no moons. Venus has no moons. The question of whether Venus ever had a moon is genuinely interesting. The giant impact hypothesis for lunar formation on Earth, a Mars-sized body colliding with the early Earth, is a specific kind of event. If Venus underwent a similar large impact, which the retrograde rotation hypothesis suggests, that impact might have either created a moon or destroyed an existing moon. One proposed scenario involves Venus having formed a moon from a large impact, and then that moon later spiraling inward and being destroyed, rather than spiraling outward as Earth's moon has done. Whether a Venusian moon would spiral outward or inward depends on the specific rotation rate and direction of Venus at the time. For a retrograde rotating Venus, a prograde moon would actually spiral inward, being decelerated by tidal interactions rather than accelerated, and eventually collide with the planet. If Venus had a moon early in its history that was destroyed in this way, the impact of that moon colliding with Venus would have been an enormous event, potentially responsible for some of the geological features we observe, potentially contributing to the resurfacing of the planet, potentially affecting the atmospheric chemistry and thermal history. This is speculative. There is no direct evidence that Venus had a moon, but it is the kind of hypothesis that could in principle be tested with better geological mapping of Venus, by looking for signatures of an ancient large impact that might represent a former moon collision. And it illustrates how interconnected the various mysteries of Venus are. Let us now talk about the very recent results from the James Webb Space Telescope that are relevant to Venus. Not direct observations of Venus itself, but observations of exoplanets that put Venus in a broader context. Webb has been observing the TRAPPIST-1 planetary system in detail. In 2023, earlier results from observations of TRAPPIST-1b, the innermost planet of the system, which orbits much too close to its star to be in the habitable zone, suggested that it likely lacks a substantial atmosphere. The thermal emission spectrum measured by Webb was consistent with a bare rock with no significant atmospheric heat redistribution. This result is relevant to Venus because it demonstrates that Webb can detect the presence or absence of atmospheres on rocky exoplanets, and is beginning to characterize the atmospheres of rocky planets in and near habitable zones. For the habitable zone TRAPPIST-1 planets, specifically TRAPPIST-1e, 1f, and 1g, the question of whether they have atmospheres, and if so what kind, is directly connected to the Venus habitability question. These planets orbit a red dwarf star rather than a sun-like star, which means the stellar environment is different. Red dwarfs produce more flares and more ultraviolet radiation relative to their total luminosity, which can strip planetary atmospheres more aggressively. Whether the TRAPPIST-1 habitable zone planets retained their atmospheres depends on factors including stellar wind, planetary magnetic fields, and volcanic outgassing, all factors we are trying to understand through the study of Venus and Mars. The TRAPPIST-1 results from Webb will continue to accumulate over the next several years. Each result, each constraint on which planets have atmospheres, what those atmospheres contain, how much thermal redistribution is occurring, adds to a picture of rocky planet diversity that is directly informed by our solar system study of Venus, Earth, and Mars. Venus as the runaway greenhouse case, Earth as the habitable case, Mars as the atmospheric stripping case. 3 different outcomes for 3 different rocky planets, a sample of planetary diversity that, while tiny, is our primary empirical grounding for the models we apply to the thousands of exoplanets now known. Let us now talk about what the next 10 years of Venus exploration will look like, about the missions that are planned, funded, or in development, and what specific questions they will address. The European Space Agency's Envision mission is currently in development phase, with a planned launch in the early 2030s and Venus orbit insertion in the mid-2030s. Envision will carry a suite of instruments, including a radar sounder that can penetrate the surface to depths of several kilometers, a spectrometer covering ultraviolet to near-infrared wavelengths, and a radio science experiment for precision gravity mapping. Envision's primary science goals include understanding whether Venus is currently geologically active, characterizing the composition and age of surface units, and understanding the planet's atmospheric dynamics and chemistry. The radar sounder is particularly significant. Ground-penetrating radar, which works by sending radar pulses into a surface and detecting the reflections from subsurface interfaces, has been used on Mars by the MARISS and CHARAD instruments on Mars Express and Mars Reconnaissance Orbiter, revealing buried ice, layered geology, and potentially liquid water. On Venus, subsurface radar has never been used. If there are buried geological features, ancient lava tubes, subsurface lava lakes, remnants of ancient terrain buried by later volcanism, Envision's radar sounder has the potential to find them. NASA's Da Vinci mission is designed to send an atmospheric probe into Venus's atmosphere, a sphere-shaped descent probe that will fall through the atmosphere for about 63 minutes, sampling the chemistry at multiple altitude levels from the cloud tops all the way to the surface. The probe will land, or rather impact, as it is not designed for a soft landing, in the tessera terrain of Alpha Regio, the oldest known terrain on Venus. The most important measurements Da Vinci will make are of noble gases, helium, neon, argon, krypton, and xenon, in the deep atmosphere. Noble gases do not react with anything. Their abundances and isotopic ratios in a planetary atmosphere directly record the primordial composition of the material from which the planet formed, the history of atmospheric escape, and any contributions from comets or asteroids. On Earth and Mars, noble gas measurements have provided crucial information about the planetary histories. Venus has never had its noble gas abundances measured to any precision. Da Vinci will make these measurements for the first time. The noble gas measurements will constrain when Venus lost its water, from where Venus's water originated, and how the atmosphere has evolved over time. They are expected to be among the most important measurements in the history of Venus exploration. Not dramatic or spectacular, but fundamentally constraining in ways that reshape our understanding of Venus's history. The third major Venus mission under development is NASA's VERITAS, Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy.
Veritas has had a troubled development history. It was selected for development alongside Da Vinci in 2021 as part of NASA's Discovery program, but its development was subsequently delayed due to budget pressures and the reallocation of resources to Mars sample return. Whether Veritas will fly and on what timeline remains uncertain as of 2024.
If Veritas flies, it would provide the highest resolution radar map of Venus ever made, dramatically improving on Magellan, and would include the infrared spectrometer capable of distinguishing different rock types on Venus's surface. The combination of high-resolution topography, precise gravity mapping, and surface mineralogy would transform our understanding of Venus's geology in the same way that the Mars Reconnaissance Orbiter transformed our understanding of Mars, from a coarsely characterized world to one whose geological history can be read in unprecedented detail. Beyond these 3 missions, there are longer-term concepts in development. LISS, the Long-Lived In Situ Solar System Explorer, is a NASA concept for a long-duration Venus surface lander that would survive for weeks or months using high-temperature electronics capable of making sustained measurements of the surface environment. The SAGE concept, Surface and Atmosphere Geochemical Explorer, would use a similar approach for surface geochemistry measurements. Russia has proposed the Venera-D mission, a collaboration that at various points has included NASA participation, which would include an orbiter and a long-duration surface station. None of these longer-term concepts has been fully funded and approved, but the scientific community's recognition that Venus is a priority, expressed most recently in the 2023 to 2032 Planetary Science Decadal Survey, which identified Venus as a high-priority target and recommended the development of both Da Vinci and Veritas, ensures that Venus exploration will continue to be funded and developed through the coming decades. We are entering what is likely to be the most scientifically productive era in the history of Venus exploration. 3 missions from 3 space agencies converging on Venus in the 2030s, each with instruments specifically designed to answer the outstanding questions that have accumulated over decades of increasingly frustrated study. What will they find? The honest answer is that we do not know. And the fact that we do not know, the fact that Venus has been systematically surprising us every time we look more carefully, is itself the reason to look more carefully. Let us talk about something that has never received the attention it deserves, the specific question of what Venus's clouds look like from the inside, and what we actually know about the particle physics and microphysics of the cloud layers that make them such a scientifically compelling environment. Most descriptions of Venus's clouds present them as a uniform layer of sulfuric acid mist, a featureless chemical fog stretched around the entire planet. The reality is significantly more complex and significantly more interesting. The cloud system of Venus is divided into distinct layers with different properties. The upper haze layer, above about 70 kilometers altitude, consists of very small particles, submicron in size, and is relatively transparent. The upper cloud layer, from roughly 57 to 70 kilometers, contains particles of 2 distinct modes. Smaller particles averaging about 0.4 microns in radius, and larger particles averaging about 2 microns. The middle cloud layer, from about 50 to 57 kilometers, contains particles in the same 2 size ranges but at higher number densities. The lower cloud layer, from roughly 48 to 50 kilometers, contains particles in all 3 size modes, including a third, larger particle type with radii around 3.5 microns. And below 48 kilometers, there is a lower haze extending to about 31 kilometers altitude. This layering is not static. Venus Express observations showed that the cloud layers vary dramatically in opacity, thickness, and structure over time, and not just gradually. The cloud structure can change on timescales of hours. Waves propagate through the cloud layers. Convective structures, analogous to thunderstorm cells on Earth, appear and disappear. The cloud system is dynamically alive in ways that are still poorly characterized. The large mode particles in the lower cloud layers, those 3.5 micron particles, are the most scientifically interesting. Their size is significantly larger than what standard photochemical models of Venus's cloud formation would predict. Sulfuric acid droplets forming purely from gas phase nucleation of water and sulfur dioxide should produce smaller particles. The presence of large particles requires either unusual nucleation mechanisms, unusual growth processes, or the incorporation of other material into the cloud particles as nucleation cores. What might those nucleation cores be? On Earth, cloud particles typically form around cloud condensation nuclei, small particles that provide a surface for water vapor to condense on. These nuclei are typically mineral dust, sea salt particles, organic aerosols, or soot from combustion. In Venus's atmosphere, there is no mechanism for producing mineral dust aerosols in the cloud layers. The surface is far below. There could be meteoric material, particles from meteorites burning up in the upper atmosphere. But whether there is enough meteoric material to nucleate the large mode cloud particles is uncertain. One proposed source of cloud condensation nuclei in Venus's cloud layers is volcanic aerosols, sulfur-bearing particles injected into the atmosphere by volcanic activity and transported upward. If Venus is as volcanically active as the recent evidence suggests, volcanic aerosols could be a significant component of the Venusian cloud particle population. Another proposed component, the one that makes the large particle problem relevant to the astrobiology question, is the possibility that the cloud particles have biological material in their cores. Certain types of microorganisms can serve as ice nucleation particles in Earth's clouds. This is well documented. Whether analogous cloud seeding by organisms could occur in Venus's clouds is entirely speculative, but it is a specific, testable hypothesis. If biological material is incorporated into Venus's cloud particles, they would have specific spectroscopic signatures distinguishing them from pure sulfuric acid. The opacity variations in the cloud layers are another area of active scientific interest. Venus Express discovered that the cloud opacity at ultraviolet wavelengths varies with a specific periodicity, about 4.6 Earth days, that matches the rotation period of the cloud layers in the upper atmosphere. This periodicity is consistent with a planetary scale wave propagating through the atmosphere. But the amplitude of the opacity variations, the extent to which the clouds become more or less transparent on this cycle, varies over longer timescales in ways that are not fully understood. Understanding the cloud opacity variations matters because the cloud opacity determines how much solar energy reaches the lower cloud levels and the surface. Changes in cloud opacity affect the energy balance of the entire atmospheric system. If the cloud opacity variations are driven by chemistry, by reactions that produce or consume the UV absorber, then they are windows into the chemical processes occurring in the clouds. If they are driven by dynamics, by changes in cloud particle concentrations driven by vertical mixing, they tell us about the atmospheric circulation patterns that move material between altitude levels. Let us now talk about the atmospheric dynamics of Venus in more detail, about the specific phenomena that make the circulation of Venus's atmosphere one of the most challenging problems in comparative planetology. The dominant feature of Venus's atmospheric dynamics is the atmospheric superrotation we mentioned earlier. At cloud altitude, approximately 65 to 70 kilometers, winds reach 360 kilometers per hour, completing a circuit of the entire planet in about 4 Earth days. This compares to the planet's rotation period of 243 Earth days. The atmosphere moves approximately 60 times faster than the solid planet beneath it. This is bizarre. On Earth, the atmosphere is driven primarily by solar heating and rotation. The difference between equatorial heating and polar cooling creates pressure gradients that drive winds, and the Coriolis force, due to Earth's rotation, organizes those winds into the characteristic jet streams, trade winds, and other patterns. The atmospheric circulation and the planetary rotation are coupled, not identical in speed, but operating in the same general direction and on similar timescales. On Venus, the coupling is broken. The atmosphere moves at a completely different speed and on a completely different timescale from the solid planet. This requires a mechanism that continuously accelerates the atmosphere, that pumps angular momentum into the atmospheric circulation from some source, maintaining the superrotation against the friction that would otherwise slow it down. The proposed mechanisms include thermal tides driven by solar heating, the daily cycle of heating and cooling as different parts of the atmosphere face the sun, and eddy fluxes of angular momentum driven by atmospheric waves. Both mechanisms have been studied in models and can, in principle, produce superrotation. But getting the right superrotation speed and vertical structure has proven difficult. Models that produce superrotation tend to be sensitive to the parameterization of small-scale processes, turbulence, wave dissipation, that are not directly observable from orbit. Venus Express discovered something remarkable about the superrotation. It is not stable. The wind speeds at cloud level measured by Venus Express varied by tens of kilometers per hour over the 4-year mission period. These variations were not random. They showed structure, with changes in wind speed correlated with changes in cloud structure and opacity. The atmosphere is not in a steady state. It is fluctuating in ways that are connected across different altitude levels and different physical processes. The Akatsuki spacecraft, a Japanese Venus orbiter that has been operating since 2015 after a dramatic rescue involving a second arrival attempt following a main engine failure, has continued to monitor Venus's atmospheric dynamics. Akatsuki's cameras operate at multiple wavelengths, allowing simultaneous imaging of different atmospheric layers. Its data has revealed the existence of a large-scale stationary wave in Venus's upper atmosphere, a bow-shaped structure stretching from pole to pole that remains fixed in position relative to the underlying topography, even as the superrotating winds flow through it. This stationary wave is produced by gravity waves, not gravitational waves in the general relativistic sense, but atmospheric gravity waves, the kind that form when air flows over mountains and creates downstream wave patterns. The Aphrodite Terra highland region, one of Venus's largest elevated regions, appears to be the source. Air flowing over the highlands at low altitude generates waves that propagate upward through the atmosphere and produce the bow-shaped structure visible at cloud altitude. The discovery of this stationary wave was important because it demonstrates a direct coupling between Venus's surface topography and its upper atmosphere dynamics, a connection that operates despite the thick, slowly rotating lower atmosphere that separates them. This coupling means that the topography of Venus is not irrelevant to the atmospheric dynamics, as might be assumed for such a dense, sluggishly rotating planet. It actively shapes the upper atmospheric flow. Let us now talk about the electrical environment of Venus, about the lightning question, and what it implies more broadly for the coupling between the surface, the atmosphere, and the cloud layers. The evidence for lightning on Venus comes from multiple independent sources, each with its own limitations. The Soviet Venera probes detected radio emissions consistent with lightning during their atmospheric descents.
The Cassini spacecraft, during its gravity assist flyby of Venus in 1998 and 1999, detected radio emissions from Venus at the frequencies expected from lightning. Venus Express detected Whistler waves, electromagnetic waves that propagate along magnetic field lines in a characteristic frequency-dispersed pattern associated with lightning on Earth, in Venus's ionosphere on numerous occasions. The counter-argument comes from the absence of detection in ground-based searches at radio frequencies where lightning should be detectable, and from the difficulty of identifying a clear physical mechanism for charge separation in Venus's sulfuric acid cloud system. A 2021 paper by Francisco Mills and colleagues proposed a specific mechanism for lightning on Venus that does not require the ice crystal collision process that produces Earth's lightning.
In their model, the sulfuric acid droplets themselves, under the influence of vertical air currents, can become charged through a process called contact electrification, where droplets of different sizes, carried at different velocities by air currents, transfer charge when they collide. This is a different charge separation mechanism from Earth's, but is physically reasonable and potentially capable of producing the charge buildup needed for lightning. If Venus has lightning, it is almost certainly different in character from Earth's lightning. Different altitudes, different frequency, different energy, potentially different spectral characteristics. The instruments sent to Venus so far have not been optimally designed to characterize Venusian lightning. They have detected signals consistent with it, but not definitive. A dedicated lightning detector, either on an atmospheric probe like Da Vinci or on a long-lived surface station, would be needed for definitive characterization. The significance of Venusian lightning goes beyond curiosity about whether it exists. Lightning is a major driver of nitrogen chemistry in Earth's atmosphere. It converts nitrogen and oxygen into nitric oxide, which is oxidized to nitrogen dioxide and eventually dissolved into precipitation as nitric acid. This lightning-driven nitrogen cycle is a significant part of Earth's atmospheric chemistry and affects the nitrogen available to surface life. On Venus, if lightning occurs, it would drive chemical reactions in the cloud layers that are not currently included in atmospheric models. More speculatively, lightning could provide an energy source for whatever chemistry is occurring in the cloud layers, including, in the most speculative version, an energy source for metabolic processes, if there is anything living there. Let us now talk about something that directly connects Venus to the question of Earth's future, about what Venus tells us about where Earth is going as the Sun continues to brighten. The Sun is getting brighter. On the main sequence, stars increase in luminosity as they age. Hydrogen fusion in the core gradually changes the core's composition, increasing its temperature and pressure, which increases the luminosity. Over the Sun's 4.6 billion year life, its luminosity has increased by approximately 30%. In another 1 billion years, it will be approximately 10% brighter than today. In another 5 billion years, it will expand into a red giant, engulfing the inner planets. But Earth's uninhabitability does not require the red giant phase. The models that suggest Venus was habitable for 2 to 3 billion years and then crossed the runaway greenhouse threshold due to increasing solar luminosity, if those models are correct, imply something important. There is a specific luminosity threshold at which a planet in Earth's position will cross from habitable to uninhabitable. The estimate for when Earth crosses this threshold varies by model, but several serious analyses place it in the range of 500 million to 1.5 billion years from now. After that point, not the red giant phase, not the death of the Sun, but the ordinary gradual brightening of the Sun, the increasing solar energy input will eventually overwhelm the carbon silicate weathering thermostat that has maintained Earth's climate stability for billions of years. Water vapor feedback will take over. Temperatures will rise. More water will evaporate. More greenhouse effect. More warming. Eventually, the oceans will begin to evaporate in a process analogous to what happened on Venus. The timeline is not urgent in any human sense. 500 million years is 100 times longer than the history of animal life on Earth. But it is a finite deadline. And Venus is our example of what that transition looks like, what the planet becomes afterward. Understanding the specific conditions under which Venus crossed its threshold, the specific atmospheric composition, the specific solar luminosity, the specific initial water content, tells us directly about the equivalent threshold for Earth. If Venus crossed it at slightly lower solar luminosity than current models predict, Earth's deadline might be sooner. If Venus crossed it at higher luminosity, Earth might have more time. The uncertainty in our Venus habitability models translates directly into uncertainty in Earth's long-term future. This is not an immediate practical concern, but it illustrates why Venus science is not purely academic. It is Earth science extended to its planetary neighbour and reflected back at us. Let us now talk about the question of what happened to Venus's water in more detail, about the specific mechanisms of water loss and what the measurements tell us about the timeline. Venus's current atmosphere contains only about 30 parts per million of water vapour, an extraordinarily dry atmosphere for a planet of Venus's size. For comparison, Earth's atmosphere contains roughly 10,000 parts per million water vapour on average. The D/H ratio, the ratio of deuterium-containing water to ordinary hydrogen-containing water, is approximately 150 times higher on Venus than in Earth's oceans. This extreme enrichment in deuterium is the chemical signature of massive water loss over geological time. The enrichment occurs because water molecules containing the lighter hydrogen-1 isotope are slightly lighter than those containing the heavier deuterium-2. When water vapour in a planetary atmosphere is dissociated by ultraviolet radiation into hydrogen and oxygen, and the hydrogen atoms escape to space, the lighter hydrogen-1 escapes more easily than the heavier deuterium. Over time, the remaining water becomes enriched in deuterium. The specific enrichment factor of 150 is enormous. Working backwards from this enrichment factor, using models of hydrogen escape rates, gives an estimate of how much water Venus has lost over its history. The calculation is uncertain. It depends on the initial D/H ratio of Venus's water, assumed to be similar to Earth's, the average escape rate over geological time, and various model assumptions. But the result consistently points to Venus having lost a global ocean equivalent. Not a small amount of water, a genuine global ocean, comparable in depth to Earth's oceans. How long did this process take? The D/H enrichment does not directly tell us the timeline. It tells us the total amount of water lost, not how quickly. But combining the D/H data with atmospheric escape rate measurements from Venus Express and models of Venus's past solar environment gives a rough picture. Most of the water loss likely occurred relatively early in Venus's history, within the first billion years or so, as the young sun's intense ultraviolet radiation drove rapid atmospheric escape. This timeline is consistent with the model in which Venus was habitable with liquid surface water for roughly 2 to 3 billion years. The water was gradually lost to space, and the climate eventually became unstable as the water inventory fell below the level needed to stabilize the carbonate silicate thermostat.
Without sufficient water to drive weathering reactions that remove CO2 from the atmosphere, volcanic CO2 began to accumulate. The greenhouse effect intensified, and the remaining water was lost in a positive feedback. The Da Vinci mission's noble gas measurements will provide the most precise constraints yet on this water loss history. Specifically, the ratio of different xenon isotopes in Venus's atmosphere is sensitive to the history of atmospheric escape. Different isotopes escape at slightly different rates, leaving a measurable isotopic signature of the escape process. Combining the noble gas data with the D/H ratio will give a much more detailed picture of when and how Venus lost its water. Let us now talk about the discovery that Venus's south polar vortex is not behaving as expected, another example of Venus doing something our models did not predict. Both of Venus's polar regions are covered by large atmospheric vortices, swirling cloud systems centered on the poles.
The polar vortex structure is expected. At Venus's poles, the atmosphere cools radiatively and descends, creating a low-pressure region that drives a cyclonic circulation. Earth has polar vortices too. They are responsible for the cold air outbreaks that bring Arctic weather to lower latitudes when the vortex destabilizes. Venus's polar vortices were first observed by Pioneer Venus in 1979. They have a distinctive double eye structure, not a single central low-pressure region, but two connected low-pressure areas that rotate around each other, creating a figure-8 pattern visible in thermal infrared images. This double-eye morphology is unusual. Nothing quite like it exists in Earth's atmosphere, and its origin is not fully explained. Venus Express, observing the south polar vortex continuously for years, discovered something unexpected. The vortex changes shape. Not just the normal variability of weather systems, the vortex shape changes dramatically in ways that cycle with periods of a few days. It goes from its canonical double eye structure to more complex asymmetric shapes, sometimes appearing as a single elongated mass, sometimes with multiple centers of rotation. These morphological changes occur faster than simple radiative or mechanical forcing could explain. They suggest that the polar vortex dynamics are connected to wave activity propagating from lower latitudes, that the entire atmospheric circulation from equator to pole is coupled in ways that transmit information rapidly upward and poleward. The south polar vortex also moves. Its center, the geometric center of the swirling cloud system, wanders around the South Pole, sometimes displaced by several degrees of latitude over periods of days. This wandering is not random. It has a coherent structure, suggesting a connection to atmospheric wave modes with specific propagation characteristics. But the specific mechanism connecting the polar vortex wandering to other atmospheric phenomena is not fully characterized. Akatsuki has been observing the north polar vortex of Venus, providing continuous monitoring that Venus Express provided for the south. The comparison between north and south polar vortex behavior reveals asymmetries. The two poles are not behaving identically, that place additional constraints on models of Venus's atmospheric circulation. A planet with a perfectly uniform atmosphere and no surface topography coupling would be expected to have symmetric polar vortices. The asymmetries are another clue that the atmosphere is connected to the surface in ways that are not fully understood. Let us now talk about what the Akatsuki spacecraft has revealed that we did not expect. Because Akatsuki's story is itself remarkable, and its scientific contributions have been underappreciated. Akatsuki was launched in May 2010 with a planned arrival at Venus in December 2010. The main engine failure during orbital insertion was catastrophic. The spacecraft missed Venus entirely and went into orbit around the Sun. For 5 years, Akatsuki orbited the Sun alone. Its mission apparently failed. Then, in December 2015, JAXA engineers executed a difficult and unprecedented maneuver, firing the small attitude control thrusters that remained functional in a long burn to bring Akatsuki into Venus orbit. The maneuver worked. Akatsuki entered Venus orbit 5 years late, in a very different orbit from the planned one, but functional. The resulting orbit was far from ideal, more elliptical than planned, with a different inclination. But it turned out to have unexpected scientific advantages. The highly elliptical orbit allowed Akatsuki to observe Venus from very different distances, providing both global context from far away and high-resolution detail from close approach. The different inclination provided coverage of portions of Venus's atmosphere that Venus Express had less frequently observed. Akatsuki's cameras operate at multiple wavelengths simultaneously, allowing different cloud layers to be imaged at the same time. At ultraviolet wavelengths, Akatsuki images the upper cloud tops. At 2-micron infrared wavelengths, it images through the clouds to probe deeper atmospheric layers. At longer infrared wavelengths, it images the thermal emission from different altitude levels. This multi-wavelength capability has allowed three-dimensional reconstruction of atmospheric wave structures in a way not possible with single-wavelength instruments. Among Akatsuki's discoveries, the detection of a large-scale bow-shaped wave structure we mentioned earlier, a planetary-scale atmospheric gravity wave fixed relative to surface topography that spans from pole to pole. This is the largest gravity wave structure ever observed in the solar system. Its existence was not predicted by atmospheric models and required post-discovery explanation. Akatsuki also discovered a quasi-stationary feature in the equatorial clouds, a bright band in thermal infrared that remained fixed relative to Venus's surface while the super-rotating winds flowed through it. This feature appears to be driven by atmospheric convection, preferentially occurring over specific surface features below. It demonstrates that even at 70 kilometers altitude, the atmospheric dynamics retain a memory of the surface topography. That surface-atmosphere coupling extends across the full depth of Venus's dense atmospheric column. The equatorial convective feature also has implications for the cloud chemistry. Convective updrafts that preferentially occur over specific surface regions would bring material from lower atmospheric levels, where the chemistry is different from the cloud layers, up into the cloud region. This vertical mixing would affect the chemical composition of the cloud layers at specific longitudes, potentially explaining some of the spatial variability observed in Venus's cloud properties. Let us now talk about what Venus can tell us about the habitability of planets around red dwarf stars, a connection that has become increasingly important as astronomers focus on red dwarfs as the most common and therefore most numerous hosts of potentially habitable planets. Red dwarf stars, M-type stars, are the most common type of star in the galaxy, comprising roughly 75% of all stars. They are smaller, cooler, and longer-lived than the Sun. Because they are cooler, their habitable zones, the range of orbital distances where liquid water can exist on a rocky planet, are much closer in than the Sun's habitable zone. A red dwarf's habitable zone might extend from a fraction of Earth's orbital distance to a few tenths of Earth's orbital distance from the star. This proximity has consequences. Planets in the habitable zones of red dwarfs are close enough to the star to become tidally locked. The same side of the planet always faces the star, creating a permanent day side and a permanent night side. This is the red dwarf equivalent of Venus's slowly rotating problem, a planet with an extreme distribution of heating between the permanently lit and permanently dark sides. Planets in the habitable zones of red dwarfs are also exposed to more energetic radiation from their stars. Red dwarfs are more active than the Sun in terms of stellar flares and UV emission relative to their total luminosity. This means more atmospheric erosion from stellar wind interactions, more UV radiation driving photochemistry in the atmosphere, and more radiation impinging on the surface. Venus is not tidally locked and does not orbit a red dwarf, but its slow rotation, its atmospheric dynamics, and its history of atmospheric erosion are directly relevant to understanding what happens to planets in these more extreme environments. The atmospheric superrotation that Venus exhibits, where the atmosphere circulates much faster than the planet rotates, is exactly the kind of circulation that models predict for tidally locked exoplanets. Understanding why Venus's atmosphere superrotates and how that superrotation affects the climate and chemistry directly improves our models of tidally locked exoplanet atmospheres. Similarly, the history of atmospheric erosion on Venus, how the solar wind interacted with Venus's ionosphere to strip atmosphere over time, is relevant to the much more intense stellar wind environment of red dwarf habitable zone planets. If Venus lost significant atmospheric material to solar wind stripping, despite being closer to Earth's distance from the Sun than typical red dwarf habitable zone planets, then red dwarf habitable zone planets face a more severe version of the same problem. This connection between Venus and red dwarf habitability is one of the primary scientific justifications for the upcoming Venus missions from the perspective of exoplanet science. Every measurement that constrains how and when Venus lost its atmosphere, every improvement in our models of atmospheric escape, climate stability, and cloud chemistry feeds into our assessment of the habitability of the most common class of potentially habitable planets in the galaxy. Let us now talk about what we know about Venus's core, about the limited constraints we have and why they matter. Venus and Earth have very similar overall densities, both averaging about 5.4 to 5.5 grams per cubic centimetre. This is much denser than silicate rock, which averages about 3 grams per cubic centimetre. The high density of both planets implies that both have large metallic cores, predominantly iron with some nickel, similar to Earth's core. On Earth, the core is divided into a liquid outer core, the region where convection generates the magnetic field, and a solid inner core. The transition from liquid to solid occurs as the temperature decreases to the iron melting point at the relevant pressures, and the inner core has been growing over Earth's history as the planet gradually cools and more iron crystallizes. For Venus, we do not know whether it has a liquid outer core capable of convecting and generating a magnetic field. The absence of a detectable intrinsic magnetic field tells us that if Venus has a liquid outer core, it is not convecting in the way that generates Earth's field. Possible explanations include: Venus's core has already solidified completely. Venus's core is liquid but not convecting, perhaps because there is insufficient temperature contrast between the core mantle boundary and the outer reaches of the core. Or Venus's core composition differs from Earth's in a way that affects its dynamics. Each of these explanations has different implications for Venus's thermal history and evolution. A completely solidified core would imply that Venus's interior has cooled more than Earth's, which seems inconsistent with the evidence for current volcanic activity. A liquid but non-convecting core would imply that Venus's interior has a different thermal structure from Earth's, and the question becomes, why? A compositionally different core is possible if Venus's formation history differed from Earth's in ways that changed the iron-to-nickel ratio or added significant amounts of lighter elements like sulfur or oxygen. The seismological data that would distinguish these possibilities does not exist. Seismic waves generated by Venus quakes and recorded by a surface seismometer would provide direct constraints on the interior structure, on the size and state of the core, on the layering and composition of the mantle. Without seismic data, we are limited to indirect inferences from gravity field modeling and surface geology. This is another manifestation of the fundamental measurement gap in Venus science. We know Venus's size, mass, and overall density to high precision. We know the topography and surface geology at Magellan resolution. We have some atmospheric chemistry measurements from the Venera probes and remote sensing, but we do not have the fundamental interior constraint, seismic data, that would tell us the most about how Venus is structured and how it has evolved. Let us now talk about something that is genuinely happening on Venus right now that no model predicted: the ongoing changes in sulfur dioxide abundance that Venus Express detected and that remain poorly explained. Venus Express monitored the abundance of sulfur dioxide in Venus's mesosphere, the atmospheric layer above the main cloud deck, throughout its 2006 to 2014 mission. The data revealed something unexpected. The SO2 abundance in the mesosphere varies dramatically. From 2006 to about 2010, Venus Express detected a decline in SO2 abundance by a factor of 5 or more at certain altitudes. Then the abundance began to recover. These large variations in SO2 abundance were not predicted by atmospheric chemistry models. In the standard model, SO2 is produced by volcanism, mixed upward through the atmosphere and converted to sulfuric acid in the cloud layers by photochemical reactions. The abundance in the mesosphere should be roughly steady, controlled by the balance between the upward flux of volcanic SO2 and the photochemical conversion rate. The observed variability requires either variability in the volcanic source, the volcanic activity producing SO2 fluctuating on timescales of years, or variability in the atmospheric transport, changes in how vigorously material is mixed between the cloud layers and the overlying mesosphere, or both. The volcanic source explanation is interesting in the context of the current geological activity evidence. If Venus has active volcanic plumes currently erupting at some of the 37 identified hotspot locations, those eruptions might be episodic, producing bursts of SO2 that are then transported upward and detected in the mesosphere years later, after the SO2 has mixed through the lower atmosphere. The timescale of the Venus Express SO2 variations, several years, is consistent with the transport timescale from the lower atmosphere to the mesosphere. If this interpretation is correct, the SO2 variability detected by Venus Express was a remote signature of ongoing volcanic activity on Venus's surface, the first detection of current volcanic activity, predating the Herrick and Hensley geological finding by more than a decade, but not recognized as such at the time. This is a common pattern in Venus science: data that contains important information that is recognized only later when it can be placed in the context of other findings. The Magellan data that showed the changed volcanic vent was collected in 1991, but analyzed in a definitive way only in 2023. The Venus Express SO2 data was collected between 2006 and 2014, but its implications for current volcanic activity are still being worked out. This pattern suggests that there is significant scientific potential remaining in existing Venus datasets, that applying new analytical techniques and new conceptual frameworks to data already collected could yield further discoveries before the new missions arrive. Let us now talk about the climate modelling work being done to understand Venus's past habitability, about the specific models and what they predict about when and how the transition from habitable to uninhabitable occurred. The pioneering modelling work by Michael Way and Anthony Del Genio, published in Geophysical Research Letters in 2016, simulated an early Venus with several key differences from today. A rotation period of 16 hours, a faster rotation that some models of early Venus suggest was possible before atmospheric tidal torques slowed it to the current rate. A solar luminosity appropriate for 2 to 3 billion years ago, and an initial water inventory equivalent to Earth's current ocean. Under these conditions, their climate model produced a stable, temperate climate on Venus, with surface temperatures similar to Earth's, with stable liquid water oceans covering most of the surface, and with a carbon cycle operating to regulate CO2 and maintain the temperate conditions. The climate was stable over the entire 50 Earth-year simulation period they ran. The conclusion that Venus could have been habitable for 2 to 3 billion years was striking because it suggested that habitable worlds can transition to uninhabitable states relatively late in their history, well after life would have had time to originate and evolve. Subsequent modelling work has complicated this picture. A 2019 study by Martin Turbit and colleagues found that when they included the effects of rotation on cloud formation more carefully, an early Venus with liquid water would produce dense water clouds on the night side that actually warmed the planet more than expected, making it harder to maintain the temperate conditions that Way and Del Genio found. Their model suggested that Venus might have been too warm for liquid water even early in its history. This disagreement between models illustrates how sensitive the habitability question is to specific physical processes, particularly the behavior of clouds. Clouds are one of the most difficult aspects of climate modeling on any planet. The right treatment of cloud formation, cloud radiative effects, and cloud circulation coupling makes a critical difference in whether a model planet is habitable or not. The Da Vinci mission's measurements of Venus's atmospheric chemistry and the Envision and Veritas missions' constraints on surface mineralogy and geological history will provide data that can discriminate between different model scenarios. If the tesserae are made of granitic rocks requiring liquid water to form, that supports the Way and Del Genio habitability scenario. If the tesserae are basaltic, that is more consistent with Venus never having had Earth-like conditions. Let us now talk about what is perhaps the single most important measurement we do not have from Venus, the measurement that would most fundamentally change our understanding of this planet. If I had to identify one measurement, one number, one data point, one constraint that would most transform Venus science, it would be the seismic velocity structure of Venus's interior. A seismogram from Venus, a single seismogram of sufficient quality from a surface station operating for even a few months, would immediately tell us the thickness of Venus's crust, the seismic velocity structure of the upper mantle, and potentially whether Venus has a liquid outer core. These measurements would constrain every model of Venus's thermal evolution, its geological history, and its interior dynamics. Knowing the crustal thickness tells us how much heat has been extracted from the mantle over Venus's history, which constrains the thermal evolution models. Knowing the mantle seismic velocity structure constrains the composition and temperature of the mantle, which tells us how similar or different it is from Earth's mantle. Knowing whether the core is liquid tells us whether Venus has or could have generated a magnetic field, which constrains the history of atmospheric protection from solar wind. The engineering challenge is extreme, but it is being taken seriously. NASA's LLI-SSE concept uses silicon carbide electronics that can operate at Venus surface temperatures. The SAGE concept uses a thermally insulated capsule. Various teams at universities and national laboratories are actively developing the technology needed for long-duration Venus surface operation. The first seismogram from Venus will be one of the most important geophysical measurements of the 21st century. Not because it will be spectacular or dramatic in appearance — a seismogram is a squiggly line on a graph — but because of what that squiggly line will tell us about a planet that we have been trying to understand for 6 decades and that keeps defying our expectations. Something bizarre is happening on Venus right now. The rotation is changing. The atmosphere is doing things our models do not predict. The surface appears to be geologically active in ways we did not expect. The cloud chemistry contains unexplained features that have resisted explanation for decades. The history of the planet suggests it might have been habitable for billions of years, and then underwent one of the most catastrophic climate transitions in solar system history. All of these things are connected. They are all aspects of a single planet that we are trying to understand from the outside, from orbit, from brief probes descending through the atmosphere, from radar maps and gravity measurements and spectroscopic data. We are trying to read the history and current state of an entire world from the signals it sends us. The signals are strange. They are telling us that Venus is not what we thought it was, and the full story of what Venus actually is, geologically, atmospherically, climatically, and possibly biologically, will require the missions that are coming, the data that has not yet been collected, and the analyses that have not yet been done. Go outside tonight and find Venus. It is not hard. When it is visible, in the west after sunset or in the east before sunrise, it is unmistakable. The brightest point of light in the sky after the sun and the moon, not twinkling like a star, steady, brilliant white, burning through the twilight with a light that feels almost aggressive in its intensity. That light is not sunlight reflected from a surface. It is sunlight reflected from clouds. You are not seeing Venus when you look at that point of light. You are seeing the tops of sulfuric acid clouds at 70 kilometers altitude, a continuous, planet-wide overcast that has never broken in all of recorded history. Whatever is underneath those clouds, the 465-degree surface, the 92 atmosphere pressure, the possible current volcanic eruptions, the geological features that were remade 500 million years ago, the ancient tessera terrain that might be the remnant of continents that required liquid water to form. All of it is permanently hidden beneath what is essentially a mirror. We built spacecraft and sent them there. The Soviet Union landed 10 probes on that surface. They survived between 23 minutes and 2 hours before being destroyed by the heat and pressure. In those brief windows, they took photographs. Flat, rocky landscapes bathed in orange light filtered through miles of dense, hot atmosphere, and made chemical measurements and detected wind noise and sent that data home before going silent forever. And then nothing landed on Venus for 40 years. Not because the planet was understood, because it was hard. Because the engineering required to survive on Venus's surface longer than a couple of hours remains at the frontier of what is possible. Because we turned our attention to Mars, a world that is cold and thin-aired and far more hospitable to our spacecraft, if not to us, and Mars has occupied the centre of planetary science for decades. But Venus has been busy while we were not looking. Not in the human sense. Venus does not know it exists, and the processes happening on its surface and in its atmosphere are not happening for any reason related to us. But in the scientific sense, every time someone goes back and looks more carefully at old data, they find something new. The Magellan data, collected in 1991, contained evidence of a changing volcanic vent that was not discovered until 2023. The Venus Express data, collected between 2006 and 2014, showed sulfur dioxide variability that may be the atmospheric signature of ongoing volcanic eruptions. The gravity data, archived after Magellan's mission, contained evidence of 37 active volcanic hotspots that was not fully extracted until 2021. Venus has been telling us things. We have been slow to hear them. What we are hearing now is this: Venus is not dormant. It is not a static hellscape that finished forming billions of years ago and has been sitting in its infernal state ever since. It is geologically active. Its atmosphere is doing things our models do not predict. Its cloud layers contain chemistry we cannot fully explain. Its rotation is changing on timescales of years in ways that connect the atmosphere to the solid planet beneath in poorly understood ways. And beneath all of that, beneath the strange present state of the planet, there is the history. The D/H ratio measuring the water that was lost. The tessera terrain that might be the geological remnant of a time when Venus had continents and possibly oceans. The model suggesting that 2 to 3 billion years ago, this planet that is now the most hostile surface environment in the solar system might have been warm and wet and potentially habitable. Might have had the conditions for life. This is not a comfortable thought. It is not comfortable because of what it implies. Venus and Earth formed together from the same material in the same solar system at similar distances from the same star. For perhaps the first half of their histories, both may have been habitable. Then Venus crossed a threshold, the exact nature and timing of which we do not yet fully understand, and the transition began. Runaway warming, the loss of the oceans, the accumulation of CO2, the destruction of whatever might have existed on the surface. Earth is still on the habitable side of that threshold. The sun has been brightening throughout the history of the solar system, and the carbonate silicate thermostat, the carbon cycle that removes CO2 from the atmosphere through weathering and returns it through volcanism, has maintained Earth's climate within the habitable range. But the thermostat has limits. The models suggest that somewhere between 500 million and 1.5 billion years from now, the increasing solar luminosity will overwhelm the thermostat. Earth will begin its own transition. And the end state of that transition, what Earth becomes, we can see right now, burning in the western sky at sunset. Venus is Earth's future in the distant sense. And Venus might have been Earth's past, in the sense of having been a world that was alive, or at least habitable, for billions of years before the transition. We are sending missions to find out. Da Vinci will descend through the Venusian atmosphere in the 2030s, sampling the chemistry, measuring the noble gases, imaging the ancient tessera terrain from below the clouds for the first time. Envision will map the surface at unprecedented resolution, peer into the subsurface with ground-penetrating radar and monitor the atmospheric chemistry over years of continuous observation. Possibly Veritas will map the mineralogy of the surface and tell us definitively whether the tesserae are made of the kind of rock that requires liquid water to form. These missions will answer questions. They will also ask new ones, because that is what Venus does. Every time we look more carefully, we find something unexpected. The phosphine is possibly there, or possibly not, and the controversy has not been resolved. The UV absorber has been unknown for a century, and the best current candidates are still uncertain. The rotation is changing in ways that no model fully explains. The polar vortex is morphing and wandering and behaving in ways that are still being characterized. The atmospheric superrotation has resisted complete physical explanation for decades. The 37 volcanic hotspots inferred from gravity data await confirmation. The single changed vent found in the Magellan data awaits systematic search for more. Every one of these anomalies is a question, and the questions are connected to each other and to the larger question of what Venus is, what it was, and what it tells us about planetary habitability in a universe full of rocky worlds orbiting stars. The universe is full of Venus-like planets, rocky planets in or near the habitable zones of their stars. Some of them are probably in the stable phase, like Earth, maintaining liquid water and moderate temperatures through some version of the carbon cycle. Some of them have probably crossed the threshold, like Venus, hot and dry and geologically resurfaced. Some of them might be in transition, crossing the threshold right now, the oceans evaporating, the climate destabilizing, the geological record of whatever was there being erased by the volcanic activity that follows. And on some of them, possibly, the transition happened but something survived. Organisms that moved upward as the surface became uninhabitable, adapting to the chemical environment of the cloud layers, finding the altitude range where temperature and pressure remained compatible with some form of biochemistry, and persisting there in the clouds for hundreds of millions of years, while the planet below became unrecognizable. We do not know if this happened on Venus. We have suggestive anomalies and an hypothesis, and not yet the measurements that would confirm or rule it out. Da Vinci will sample the atmosphere at the relevant altitude. It will look for the chemical disequilibrium that would be most suggestive of biology. It will measure the particle properties that might distinguish biological from chemical aerosols. It will not definitively answer the question, but it will dramatically narrow the space of possibilities. That white point of light in the evening sky is not a simple object. It is one of the most scientifically rich and most poorly understood bodies in the solar system. It is our nearest planetary neighbour. It is almost our twin. It has been visited by dozens of spacecraft and yet remains full of fundamental mysteries. It is currently doing things, changing its rotation, varying its SO2 abundance, showing geological features that appear to have changed, that our models do not predict. Something strange is happening on Venus right now. We are just beginning to understand what, and the most interesting discoveries, the ones that will most fundamentally change how we think about Venus and about planetary habitability and about the possibility of life in places we never thought to look, those discoveries have not been made yet. They are waiting in the cloud layers of that brilliant white point of light.